times the square, you will get it. But using de Morvier's rule, look at de Morvier's rule here. What does it say here? Given what? Complex number in polar coordinates, okay? Now, before the polar coordinates, what would you think about? You see this number? This is the x component. What is the y component here, by the way? 1. It's by default 1. Now, to which quadrant this belongs? To which quadrant? So x negative, y positive. Second. So what would you expect theta to be there in terms, let's say, of degrees? Between 90 and 180, right? Okay. Notice that here, if you have square root of 3 minus I, it will be in the 4th quadrant. Then you expect the angle between 270 and 360. Okay. So this is the first, let's say, approach to this problem. So it is in quadrant 2, and hence theta is somewhere between 90 and 180. Okay. In terms of degrees, pi over 2 and pi in terms of radian. Okay. So this is the first thing. Now that means here, now it could happen that, and I assume it will happen if you plug in here negative 1 over square root of 3, you will be getting a negative angle. That means if it's a negative angle, it means in the other direction, like we did when we did it for the Cartesian coordinates. You remember that? Okay. So to be able to use de Morvier's theorem, we need to transfer this into the form. Let me just scroll it down a little bit. In this form. That means we need to know theta and we need to know r. R is very simple and straightforward. So first thing, z in polar form. You need r, which is negative square root of 3 squared, right? Plus 1 squared all under the root. And this is equal to, what is negative square root of 3 squared? Negative square root of 3 squared. Sorry? 3 plus 1. So r is equal to 2. Now theta, what is theta? Theta equals tangent inverse of, this is the rule, y, which is 1 over square root of 3 negative. Anyone can evaluate it, please, using the calculator. What did you get? Tangent inverse of 1 over square root of, or negative 1 over square root of 3. Pi over 6 or negative 30, negative, right? What did you get? 5 pi over 6? Interesting. Yeah. So that means here the number I have here in this quadrant, right? So this is z. Now I'm looking for this angle. You remember we agreed that the angle is usually measured starting from the positive x-axis. You remember we agreed on that. So this is, now if you evaluate it in negative, this is the let's call it alpha, and this is the negative 30 I got, right? Because it's the if you like, this is counterclockwise, so this is clockwise. So it's negative, it means it's the opposite of the direction we agreed on. So that means, what is my theta here in this calculation? Sorry? -180 minus 30, right? So this angle is all 180. This is 30. And if it's negative, it means it's a shortcut from the axis. That means this angle I'm looking for is 150, or someone mentioned here, notice that 30 is pi over 6, right? So pi, so it's 5 pi over 6, right? In radian. Okay? So it will be 3 something. Okay, this is an important step here. If you manage to write this number as, so z equals to r, which is 2 times cosine of 150, let's take it in degrees, plus I sine 150. We're not done yet, but this is a big step forward to transfer it into this format. Now notice here, notice you can actually try it out. Yeah, I told you always. Question, guys? I told you always, it's always a good attitude to verify your answer. Now you can go a step further and check, is it really what I'm going to get here? I don't know, square root of 3 is 1 point something, right? Of course, this you can get it into decimal format, right? Now you can break down this here again, yeah. You can just evaluate cosine of 150 and then multiply it by 2, and then plus I sine of 150 multiplied by 2, and see whether you will be getting the original number we started with, z. Because it must be equivalent that either way I still have it here up there, it's going in both directions. Okay, so if you have the polar, you can get the standard and so on. Okay, up to getting this red framed equivalent polar. Anyone has problem with that? Problem? Okay, let's see the guys online. -30, great. So from -30, getting the fact that the angle in the positive direction is 150, sorry, is clear, or 5 pi over 6. Got it, guys? I see some skeptical. No? Okay, if you done it, we are already done actually. If you did this, so what we are going to do here, let me do it on this step here. I want to evaluate z to the power 6. So here, according to the Mervier's rule, I'm going to multiply by 6. Here I'm going to multiply by 6, and then this is to the power 6. We are done actually. Yeah? 2 to the power 6 is 2 times 2 times 2 times 2 times 2. So informatics students must know it. 64, yeah, 64. Okay, so this is equal to 64 times cosine of 6 times 150 is, I don't really know, really. It's one, is it 900? 300? Yeah, 900. Plus I sine 900. Now I told you, I don't know whether you know the function mod or modulo. You should be taking this in informatics, maybe later. Modulo. You know what's modulo? Never heard about it? Guys online, modulo function. It's actually the function that delivers the rest of dividing two numbers with each other, right? Now, why I'm asking this, 900 here is actually, where is, maybe I want, sorry for the guys online. I hope you, or maybe I can just switch to the camera. I hope. You can see something here. Okay, guys, I want someone to come to, yes, now you can see us here. I want a volunteer here to come to this board here, and you can see it. Difficult. Okay, no problem. I will just rotate it. Okay, I will put it on the paper there. No problem. Yeah. Six is from the assignment here. The you see the this is what we are going to evaluate. Okay. So remember the assignment here is to evaluate this number to the power 6, a complex, an exponent of the complex number. So we assume that this number is z, we transferred it into the polar form, and then we applied the de Morvier's theorem. Here, it is part of the assignment. Okay, now I want some volunteer here still, or maybe here, to draw this angle. What is it, this angle? 900. Theta equals 900. Any volunteer? No? You want to try it? Yes. Now notice here you just make use of the property that the function you had you are studying PPP? Yes. You had chemistry or what is it? No, it's just that it's just yeah. Okay, no problem. So now just for your information, we introduced the Morvier's rule to evaluate the exponent. Okay, great. Okay, so let's add them up. 360, one circle, right up to here, then 720, and then you agree? Okay, thank you. So you see here, this is what I told you. If you divide this by 360, what do you get? This is 2 times 360 plus 180, right? Right? So this is the rest. This is the so-called the mod function, which gives you the rest of dividing two numbers. So this is actually, this means that the angle 900 behaves exactly like the angle 180, because you have this property of the function here, the trigonometric functions, what we call it periodic. Yeah, we started with chapter 1. I think we said that some functions are periodic. That means they repeat itself after some period or some number. And this is exactly a 180. Okay, so of course you can go and plug it into your computer, and what do you get? What do you get? Let's simplify it. So z to the power 6 equals to, we said 64 times, let me just write it again here, cosine 180 plus I sine 180. Now, I don't know whether you learned at school how to evaluate the sine and cosine. Now, if you are on the, maybe we still have it here. What's the coordinate? This is the angle here, right? What is the coordinate of this point? It's -1 and 0, right? Which one is sine, which one is cosine? I think cosine is -1 here. Is it sine cosine or cosine sine? Is cos of 180 equals to 0 or -1? So your colleague online is saying -1 is cosine, right? Is it cos? So 64 times -1 plus 0, right? And this is -64. So you see how easy it is to get. Okay. So for your colleague who you had to leave, is it okay what de Morvier's rule refers to? So as you see here, it's really a great assistance here. De Morvier's rule enables us to evaluate the exponents of any complex number very, very, very easily. Okay. Now we have more assignments, but as I told you here, the key is to evaluate the corresponding angle and the magnitude of the complex number. So I don't know here, I see some faces. I assume they have questions, but don't. Anyway. Okay. So everyone agrees here for this calculation. Now let me move a little bit further, and of course, wherever you have exponents, you have the reverse of the exponent. What is the reverse of the exponents? Logarithms. Okay. Now here the thing is, we will study the exponential form, but as you saw here in de Morvier's theorem, we just restricted ourselves to the fact that n is a natural number. What if n is not natural number? Meaning, what if we have a fraction here? Let's say, and if we have a fraction, then we have what? What does it mean? C to the power 1/2. What does it mean? What does it mean, z to the power 1/2? Sorry? What is z to the power 1/2? X to the power 1/2. What is x to the power 1/2? What is 25 to the power 1/2? Sorry? Square root, right? Now, how to evaluate the square roots for complex numbers? Evaluating the square roots of complex number is very, very difficult and easy at the same time. So roots root is extractions of complex numbers. But before that, let me just remind you, what is a root? A number, what does it mean 5 is a root of 25? That means if you square 5, you will be getting 25, right? A number u is called an nth root. So nth root of another number z if u to the power n is equal to z. So this is the definition of the root, actually. Yeah? This is the definition of, okay, 5 is a root of 25. That means 5 to the power 2, or you say 2 is a third root of 8. Okay, that means 2 to the power 3 is equal to 8. So this is here is the same. Now we want to derive using de Morvier's rule, derive a formula for roots. Okay, deriving a formula to evaluate roots of a complex number, let's say z. Okay. Okay, so let's assume that z is given, of course, here, as I told you, we want to use de Morvier's rule or theorem. So z, we assume it's just given as a polar coordinate, or here I sine theta. And let us take another number, we call it u, and this u is equal to, let's assume another number, let's call it here p times cosine of another angle, maybe you call it here alpha, just to distinguish, plus I sine alpha. Okay. Now we say that u is a root of z. What does that mean? That means z equals u to the power n. Okay. Notice that this z equals, maybe I will write it here up. This is here equivalent to u equals to z to the power 1 over n. Okay, so that's why u is an nth root. So these two are equivalents here. So you can say 2 is a third root of 8, or 2 to the power 3 is equal to 8 are equivalent. So this is the meaning of the fact that one number to the power n is equal to the other, is just like if you take 1 over n as a root, you will be having the number. Okay, so that means here, let's apply de Morvier's rule. Okay. Rule or theorem. So what will we get? Z is equal R times cosine. I'm just plugging in what I assumed up there. So Z sine theta is equal to u to the power n, so I have here p to the power n, right? Cosine n times alpha plus I sine n times alpha. I hope. So here I have n, as you see here, just using De Morvier's rule here. This is, of course, equal to now. If we compare these values here, that means here you compare r with p, cosine with cosine, and so on. So here in this case, the equivalence require that r equals p to the power n, which is a real number here. It's not complex number anymore. And what does it mean n? Theta equals n times alpha. What does it mean that theta equals n times alpha? Now here you remember that the angles or the trigonometric functions are periodic. And what's the period there? We just had an example. What is the period there? So we said here that r is equal to p to the power n, and theta must be having a relation to alpha. But since we can't say it's equal to n times alpha, because the angle or the trigonometric functions, they are periodic, any multiple of 2 pi will also do this, satisfy this condition. That's why we can add any number here, and still this is sorry, k times pi. So we can add any 2 pi, any multiple of 2 pi. We are there. We just saw here in this example, is still on the board, that 900, it's twice. Sorry, I need to move this here. 900 is twice times pi plus theta, right? So here, no matter how many angles you add, how many full rounds of 2 pi you add, you are still at the same angle. Is it clear? You say here, this angle here, this is the angle, okay? This is theta, okay? But it's not only valid for theta, it's actually valid for theta plus 2 pi. In this case, k is 1. Theta plus 2 times 2 pi, 4 pi, 6 pi, and so on. So that's why this multiples of 2 pi here will be still a solution of this angle equation. Now, what does that mean here? If we solve this one for theta, if we solve this one for theta, you will be ending up of having. So here, if we solve for theta, what do we have? N alpha minus 2 pi k. And if you divide by n, you might get alpha minus 2 pi k over n. Now, what does that mean for our roots here? That means here you have as many roots as you have in the original function, where you just plug in k from 0 to n minus 1. And these are the roots we are looking for. So here, k here, if you like, is just Here, if you like, k equals 0, 1, 2, etc. Actually, here it ends at n minus 1. So here, k, this k here, this k, how many times I have this number here? This sequence, how many numbers does it include? From 0 to n minus 1. Sorry? No, let's assume n, in general n. So I'm just repeating this. Let's take a concrete example. If I'm saying 0 up to, if I find the fifth roots, so it's 0 up to 4. How many values I have there? 0, 1, 2, 3, 4, 5 values. Okay, so always when you start the index from 0 to n minus 1, then you have n values. You have n values. So I admit this is a little bit very much different than evaluating the roots of, let me see. Okay, it's different than evaluating the roots of the normal functions or normal numbers. And we will derive the formula for the roots. So, by the way, here, let me just go to the previous page. Here, from this one here for the normal number, here that means r to the power 1 over n equals to p. Okay, so here r to the power n is, so to speak, p is equals the nth root of r. Okay, so this is the meaning of 1 over n root. So as you know, you can just transfer an exponent into a root. If anyone has problem with this one, I can just repeat it. Okay, so here, if you say third root of 8 is equal 8 to the power 1 over 3. So this is roughly what this notation is saying. R to the power 1 over n is the nth root of r. Okay, that means if we want to evaluate the nth root, to evaluate the nth root, to evaluate the n distinct nth, it's terrible notation, but roots of a number, complex, of course, z, where z is given in polar coordinates, of course, as r times cosine theta plus I sine theta. If we summarize the rule we got before, or the equation, then we have z sub k, this is equal to r. You can say it's the power 1 over n times cosine of theta over n plus 2 pi k over n plus I sine of the same. Okay, theta over n plus 2 pi k over n. And then we close the square parenthesis here. Now here, important here that this k, it's just, is, if you like, is just, how is it called? An index, right? So it runs from 1 to up to n minus 1. This is important. So here, if you like, in this formula, K is a counter, yeah? So here you have K, you plug it in here. Okay, so for instance, if you want to evaluate the three distinct third roots, you evaluate Z0, Z1, Z2. So you run this index from 0, you plug it in first time 0, second times 1, third times 3. Okay, so you have always n minus 1 is the last term of your index, and you just plug it into this one here. Now, what you need to know for this calculation, we will have an example. So, for instance, you need to know from the problem, a typical format. We are not going to solve it, but a typical question here might be something like that. Find the 5 distinct fifth. So this is a typical, let's say, roots of, let's say, the number that we had before. Okay, so this is the question form, yeah? And then the question may go further, and this is, say, plot the roots on the complex plane. Complex plane, the XY plane. Okay, now regarding the first one, I see many students, they just mix up two things here when it comes to evaluating complex numbers. First, the exponent. So for instance, like the question we solved before, z to the power 6, you just plug in 6 in the De Morvier's theorem. But if you want to find the 6th roots, then you need to plug in this theorem and let the counter run here from first time you plug in 0, second time 1, 2, up to n minus 1. So here in this particular example here, it tells you here, it tells you to evaluate Z0, Z1, Z2, Z3, Z4. Okay? So these are 5 roots. So here, notice that I have n equals to 5. So this is, here it ends at n minus 1. So I evaluate it up to n minus 1, which is 4. And what I do, I plug it into here. To start with, again, I need to find the polar format or polar correspondence of my number here in this problem. We found it actually in the previous step. Okay. Any questions regarding these Z sub K roots, Z1, Z2, Z3? If you are to evaluate the 10 distincts, believe me, this has a very, very nice application in quantum physics. I don't know whether you heard about the so-called, I think they are called harmonic series. Have you ever seen this nice just like picture, like the axis, and then you have dashes, just like a flower. Anyway, now when it comes to plotting, this is interesting here. Plotting means that you have equal let's say, distance of roots. What does that mean? Equal distance of roots. You have always 360 over n angles apart. So I just write this informally. That means here, when you plot these roots, you won't be having something like, so you, for instance, this can be Z0, okay? You can't be having Z1 here and then Z2 here, for instance, if you are evaluating the three roots. This angle here between the roots is exactly equal to this amount. That means here, if I'm evaluating the 5 distinct fifth roots, what is 360 divided by 5? 360 divided by 5. Come on. 72, yeah? 72. So you will be having, when you are ultimately plotting these roots, the full cycle 360 will be evenly distributed. This is an important thing because there is another method. You can find, let's say, a starting route or an initial route, and from there, you just move this angle around to get the other roots, okay? So here, for instance, if it's 5, then you have 72, 72, 72, 72. So the five roots are evenly distributed. If you have 3 roots, then you have something like the Mercedes, how you call it, star, right? You have 3, and each angle between the roots is how many degrees? Namely 120, exactly 120. Okay, so here you have, so for the 3 roots here you have 120, 120, 120. So what I'm saying here, even if you have n roots, you can have the 360 roots, then you will be having each one is 1 angle away from the other. Even in physics, it can go in the micro, whatever, then it will be evenly distributed. This is important because I see sometimes in the exam, some students, they just plot it and then they have 2 roots very close and then the third. If you just manage to get it. Now, how to plot it? You just evaluate this value here, and ultimately, whenever you plug a number for K, with 0, 1, 2, you'll be having here an angle. And this angle, you just evaluate it and then multiply it by the root of the magnitude here. Where is it? And then you will be having coordinates. You will be having, so before you plot it, you need to evaluate it in which format? Which format you need to evaluate it? In the standard format, right? Because when you plot, you need X and Y coordinates. I know this might be confusing to some of you, so that's why let's start with a simple one, which is what we call root of unity. Okay, so I will just state this fundamental theorem of algebra. I hope I have it here somewhere. Okay, so this theorem says the following. Every complex number has exactly n distinct nth roots. Distinct means they are unique, so they can't be overlapping. Okay, nth roots, which is this one is actually an equivalent to the fundamental theorem of algebra, because notice there is a close relationship between finding the roots and solving a polynomial equation here. Because I will just write it here just to show you what does it mean to evaluate x to the power n minus 1 equals to 0. Okay, so just like I am finding n different values that satisfy this. So you can just write this x to the power n equals 1, or you can say x equals 1 to the power 1 over n, okay? Or the nth root. So this is, if you like, a modified version of the so-called fundamental theorem of algebra. And now I stress here under complex numbers. Now you will be surprised with the next example. When we are operating under the equation, under the complex numbers, you have okay, so let me just give you a simplification of the formula above. Okay, note if z equals to 1, we talk about the so-called root of unity. And in this case, z to the power n minus 1 equals to 0. Now, in this case, of course, the formula, so we don't have so if I have 1, which angle is that? So it's 0. So theta is equal to 0, right? So in this case, theta is equal to 0 and r is equal to 1. So I modify the roots formula here. So z sub k equals, so p to the power whatever, the any root of 1 is 1, so no need to write it. And then we end up of having cosine n pi k over n plus I. It's just a modification of the previous. And this is not n, of course, this is 2 pi. 2. This is 2, and down here is n. Okay. So this here, this is what we call the root of unity. It's a special case of the previous formula where we have here p or r is equal to 1. So this any root of 1 is 1. So, and here, of course, theta is equal to 0. So no need to add it or subtract it. And this is, we are going to use to evaluate the following example. Z equals 1 to the power 1 over 5. Sorry, any problem? This is 2 pi. Sorry, 2 pi. It's 2 pi. Okay. Or find the 5 distinct roots of 1. So this is just the same. Or you can say also z to the power n or solve. So I will give you another formula for that. Solve z to the power n minus 1 equals to 0. So these three formulations are equivalent. At the end of the day, we are looking. So this theorem, what I had before, the so-called fundamental theorem of algebra, it says that the number 1 has 5 distinct fifth roots under the complex number. So we know one of these roots for sure, which is what? The real, what is the fifth root of 1? What's the number if we multiply it with itself 5 times will give us 1? 1. So this is 1, which is real. So you might start from there and then move. Now here we are talking about fifth roots. How many angles we need to rotate here? Remember the formula, 360 over n 72. So this is another way to evaluate these roots. So you started at 1, then you move 72 degrees to find the next and the next and the next. But let's evaluate this using the formula, okay? So the first root, and here, I'm sorry, I forgot it. Here, of course, k runs from 1 to n minus 1. So this is important also together with this formula, okay? So now this means here, in other words, I need to evaluate. So this is my k here runs from 1, 2, 3, and 4. Okay, I'm evaluating the 5 distinct roots. That means this is my k. I just plug it into the formula. Very easy. So here you have z sub 0, z sub 1, z sub 2, and z sub 3, z sub 4. Okay, now here in the first formula, if I plug in cosine 0 over n, so 0 plus I sine 0. Okay, the second one, cosine of 2 pi 1 over 5 plus I sine 2 pi over 5. Okay, which is, as I told you, the angle 72, sorry. This one here, I will add another 72. So it will be 2 pi times 2, which is 4 pi over 5, plus I sine 4 pi over 5. Now this 4 comes from multiplying 2 pi times 2, okay? So I started with 0, 1, 2. Now the next step, I will be having cosine of 6 pi over 5. 6 comes from 3 times 2 pi. 3 times 2 pi. I sine 6 pi over 5. And last one is cosine of 4 times 2, 8 pi over 5. Plus I sine 8 pi over 5. Good. Now, obviously, if you evaluate the first one, what is cosine 0? What is cosine 0? It's cosine 0. 1 plus 0 times I is equal to 1. So this is the first root, which is the real root. Now here you can evaluate sine and cosine. Let me see if I have here if I evaluated them. So you can go further and evaluate this either in degrees or in pi. Then you will be having four coordinates. Now the thing here is that, as I told you, these 4, forget about the real root here. These 4 here will come in pairs that are conjugate to each other. Okay, that will come conjugate to each other. If you know this, will help you while plotting. So if you want to plot this, it will look something like that. So first of all, the let's say the first root, it will be on the, so this is 1 here, right? Let's say it's here, 1 and 0. Now you move here something like, I don't know. Let's take something like a circle here. So here maybe 72, the second root. So if you like, this is Z0, this is Z1. And here again, as I told you, it's conjugate will be another root. Then 72 plus 72 is how much? 144, right? So 144 will be somehow here. And this is its conjugate will be somehow here. So here, important here is I have here these roots, 1, 2, 3, 4, 5, and they are evenly distributed. That means here this angle is 360 over 5, 72. This is 360 over 5, 72. This is 72. This is 72. And this is 72. That means even without knowing the formula, if you start here with 1 and you just rotate from 0 to 72, you find out this coordinate is cosine 72 sine 72. This is cosine 72 plus 72 times sine and so on. But if you want to plot it, always think about it that this cycle here, this cycle is simply 360 is distributed exactly evenly. So each root is evenly apart from the other root. Okay, so this is just an example how to evaluate it. And we have 11:15, right? Okay, so we can talk a little bit about the so-called Euler's or exponential distribution. But there is any question here regarding this? I can imagine that this is maybe the most, let's say, not confusing, but this is a little bit different than in the real analysis. Do we do this calculation in radians or degrees? Yeah, this is actually a good question. This calculation, you can do it in radian or in degrees, but when you do it in degrees, you need to transfer 2 pi into 360, okay? You just transfer it into 360. Okay, but okay, but if I will tell you later, when you use the exponential form, it's better if you do it in radian, okay? If you use it in the exponential. Now, before we start, you can do either De Morvier's theorem or this roots evaluation using either the polar or the exponential format, okay? What is the exponential format? If you don't have any question, we can move to the exponential format. And this goes back to the famous Swiss mathematician Euler. Or it's of complex numbers, of course. Okay, so Euler's equation Okay, so given e to the power I theta is equal to cosine theta plus I sine theta, where theta is given, this is important, in radians. Hmm. And actually, it follows directly from the so-called Pythagorean theorem. So if you have here the unit circle, so if you have the unit circle, then you will be having something like that. So you have here the point. Okay, so if you like, this is, if this is unit circle, so this is one unit. So here you have cosine theta, this is theta, and this one sine theta. Okay. Now if you square cosine theta and sine theta, you will end up of having according to the so-called Pythagorean theorem, you will have the radius here, which is the famous inequality or equality in trigonometric functions. Cosine squared plus I squared is equal to. Now notice here that if you have if you have n here, if you just repeat it 2 pi, then you will be ending up. So again here, since this, let's say, because of the fact that the trigonometric functions are periodic, it follows that also this formula here is periodic. That means it will repeat itself each 2 pi. Now, because of this one here, you can also multiply by r, if you know r. So you can multiply this by r, and then the right-hand side also will multiply it by r. So here, this formula is basically for an angle, or sorry, a circle that has 1 as a radius. Okay, now how to evaluate roots? Maybe I don't know with which one you like more, but evaluating roots, you can do it in both. I will give you the formula. As I told you here, you can also here, if you multiply by r, and this you multiply by r, so then it's also, it can be generalized not only for 1, it's for any number, any positive number. Okay, now I will give you the formula or the version. Roots formula. So this is by the way, it's called the exponential form of a complex number. So wherever you have a number, a complex number in polar coordinate, the corresponding exponential form is just this here. Okay, you know theta, you know r, you just write r times e to the power I theta. That's it. Okay, roots formula using exponential. And also when you think about exponential form, or so z sub k equals to now of course here you have r to the power nth root of r, and then you have Okay, so here you have E to the power I times theta over n plus 2 pi k over n. Okay, it follows actually directly from the other formula, k equals 0, 1, 2. But here, please be careful. When you work with this formula, this theta, sorry, this theta here is in radian. Okay? So that means here, if you want to evaluate the roots, either you use this formula and here theta and radian. So this is the second formula, or you use the formula that we used before, which is this formula. And here you can either, you can use theta as degrees here, okay? And both are equivalent. So meaning it's up to you which one you feel more comfortable with to evaluate the roots. You just do it. For instance, if we want to use this, what was the angle in the previous question? 5 pi over 6, I think, right? 5 pi over 6. Okay, so shall we solve question quickly, maybe before the break? Don't know whether we will make it in 4 minutes. No. Okay, let's leave it for next time. And then I will print the worksheet for you. Okay, so after the break, you try the worksheet and let me know if you have any problems. Guys online, do you have any problems, questions? Questions? Yes, yes, we will be doing more examples. Okay, okay. We will do definitely more examples. Yes, tell me. Okay, guys online. Yes, okay. More examples. Okay, regarding the guys who online who are asking about how to apply the formula, we will be having next week an extensive worksheet for that. Uh, okay, for now, we will focus on this worksheet number 4, which is basically dealing about the basic operations. I think there's some multiplication there and simple division. Now, regarding this formula with the roots, you need just to decide on which of the formulas you are using, exponential or the polar formula. And then depending on how many roots you are going to evaluate the K is an index that you will be running up to n minus 1. For instance, if you are evaluating the fifth roots, then your K runs from 0 to 4. If you are evaluating the seventh root, K runs from 0 to 6 and so on. Okay, but don't worry. You can't hear. Guys, can you hear me?
Yes, sir.
Yes, okay. So now please just go to the island and get worksheet number 4 and start solving. If you don't have access, it's here on the projector. First, okay, and just write in the comments or ask if you have any questions regarding any of the assignments. Sorry, again. So the question from Bahani online. Okay, you square the complex number and then multiply it with the square of the conjugate. This is meant with this part E of question 2. I hope you could hear me and it's clear. Is it? Okay, you're welcome.